Hello and welcome. We're going to talk about motion in two dimensions. But first, I want to lay out a couple of things. So, as I've said before, this is my first time teaching this class, so I'm not committed to any specific way of teaching it. We've had 2 weeks. Neither have been entirely my goal for a typical week with two asynchronous days and two in-person days. But you have had a taste of both in-person and asynchronous days. I would love to hear from you on whether you feel like things are working or not. I made a survey for half the points of a post-lecture assignment. You will get credit if you simply submit the survey, but I would really appreciate your feedback. And I'm going to leave the survey open for a while, but I want to take on your feedback right away. So I do intend to discuss the initial results in class tomorrow and then potentially on Thursday if we get more responses by then. So if you have ideas right now, you can fill out the survey. And then, for example, if you think of something else later, you can submit it again. But my goal is to make this class more collaborative and something that feels worthwhile and sets you up for your future physics classes. So again, to get credit, you just have to submit the survey, but I would also really appreciate your thoughts, even if it's just, so there's one part where you say whether or not you think parts of the course are working. And then there's spots for you to expand on that. So even if you just do the first part, that would be helpful too. And you will still have a regular post-lecture activity today. It's not super long, because those are for practicing the topic. So anyway, check out the feedback survey. Plan for this lecture. I'm going to talk about vectors in two dimensions. And then perpendicular motion. Yeah. So we have the situation. It's like a city block, I guess. Someone starts here, they walk 9 blocks east, and then they walk 5 blocks north. And we want to know what their displacement is from their starting point. So not the full distance that they traveled, just the displacement, which would be this kind of arrow here. Or you could also think of it as the bird's eye view or the helicopter path, which is what your textbook brought. So yes, this tells us what the helicopter path is, but we're going to walk through how this works really quick. So reminder of trig stuff. So we have a triangle. If this is our angle, then the adjacent side is the side right next to the angle. The opposite is the one across from the angle. And the hypotenuse is the long side. And sine of the angle is the opposite divided by the hypotenuse. Cosine is adjacent divided by hypotenuse. Tangent is opposite divided by adjacent. And then if we want to solve for the hypotenuse, like if we have the opposite and adjacent, it's the square root of a squared plus O squared. So adjacent squared plus opposite squared. So now to find this 10.3 blocks, this is how you do it. You use this equation for the hypotenuse, and we have 9 blocks in one direction. In the this one's the adjacent direction because we have this angle here now. And then so that's squared plus 5 blocks, which is the opposite side, and that's squared. So you end up with 10.3 blocks as the displacement or the path of a helicopter. Also, let's see how we could find this angle too. So this one will be tangent, and remember tangent is opposite over adjacent. And to get the angle, we take the inverse tangent, which on your calculator, if you have like a graphing calculator, you should just be able to hit like second and then tangent, and that will give you, it'll pop up with a symbol like this. If you need help figuring out how to do something like that, let me know. So anyway, if we plugged in 5 blocks and 9 blocks, and then we'd get an angle of 29.1 degrees. Cool. So for one thing, this is motion in 2 dimensions. So instead of just one straight line direction, we're moving in 2 different directions now. So now I have an example problem. I actually have 3 example problems, so I might just go through all of those without coming back to the slides. But this one, we have this a vector acceleration usually. Well, yeah, and units of meters per second squared is acceleration. So it's 30 degrees down or counterclockwise from the x-axis, and it's 6 meters per second squared. So we're going to find what the x and y components are, and we will do that. No. Okay, here we go. So let's draw the x and y component. So the x component is here, a sub x, and then I'm going to draw this as a triangle, but you could also draw it along the y-axis like that if you wanted for the y one, but I'm going to keep it as a triangle because I feel like that'll be easier for us right now. A, y. Okay, so x is the adjacent side, so that means it'll have the cosine. So the x component adjacent over hypotenuse. And now we want to solve for the x component, so we will just multiply both the hypotenuse or the total acceleration on both sides, and we will get the x component equals acceleration times cosine of the angle. So that is 6 meters per second squared cosine of 30 degrees, and this is 5.2 meters per second squared for the x component. So then the y component is going to be opposite the angle. And that's sine, and sine is opposite over hypotenuse. So we just do the same thing again, multiply the acceleration on both sides. I'll do it a line lower. So the y component equals acceleration times sine of the angle. So that is 6 meters per second squared, sine of 30 degrees. And that one is 3 meters per second squared. So that's how we find the x and y components. Here, 5.2 meters per second squared and 3 meters per second squared. Cool. So like I said, I have some more examples, so we're just gonna go straight to those. This next one, we want to find the total displacement of a person who walks the following paths on a flat field. First, she walks 25 meters in a direction 49 degrees north of east. Then she walks 23 meters heading 15 degrees north of east. And then she turns and walks 32 meters in a direction 68 degrees south of east. So let's first of all just kind of define those displacements. So the first one is 25 meters at 49 degrees northeast. The next one is 23 meters at 15 degrees northeast. And then the last one is 32 meters, 68 degrees southeast. So remembering north, south, east, and west, north, south, east, west. So then I'm going to draw the vectors of each of these. Just, I feel like it'll make it a little easier on us. So first I'll draw the coordinate axis, and so this is east and this is north. So this one, and please excuse the angles. I'll try my best. I'm not good at like for the most part, not that good at estimating angles. So we'll say this is 49 degrees. This is 49 degrees, I guess. And this is vector A. Okay, and then I'll draw each of these in their own space. So this one, okay, east, north, and 15 degrees. So let's say that maybe 15 degrees, and that's vector B. And finally, vector C is southeast. So it's going to be in this quadrant where we have east and south. And then it's 32, so it's longer, and then 68 degrees, so that's pretty far over. So maybe something kind of like this. Probably not. That's probably not a big enough angle, but it's okay. 68 degrees, and this is vector C. So the thing I want us to do, actually, yeah, we'll do this part first, is let's just find the x and y component for each of these. So, right, a sub x and a sub y, and we're using, let's see, I think, yeah, for all of these, the x component is going to be cosine. So x equals the vector, I'll just put it as a for right now, cosine of the angle, and then y equals the vector times sine of the angle. So, and if you're confused with that equation, just go back to the last example. Okay. So a sub x equals a, which is 25 meters, times cosine of 49 degrees. So for this, we get 16 meters. And y, we get, again, 25 meters, but sine of 49. And this one is, I'm going to round up for this one, so it's 19 meters. Next one, bx, so 23 meters, cosine of 15 degrees, and that gives me 22 meters. And y, 23 sine 15, and that's going to be, and I'm rounding up again, 6 meters. Okay, and the last one, now, oh, I didn't draw these guys. Here's your x1 and your y, and then, that didn't work. There-ish? Yeah, close. Cx and then y, and you notice that the y component here is pointing down. That means it's going to be negative. So the x component is going to be 32 cosine of 68 degrees, which is 12 meters. And then the y one is 32 sine of 68 degrees, which is 30 meters when we round. Cool. Okay. Oh, and it's gonna be, it's negative because it's down. So gotta remember that part, because the calculation's not gonna give you that when we're using the angle the way we are. Okay, now what I wanna do is down here, draw our vectors to the best of my ability. It's not gonna be perfect, but that's okay. So let's see, we'll say something, maybe not quite that. That is vector A, and then vector B is gonna be this, and then vector C is down, so maybe something like this. Okay, and then the actual important part of that is that we can then put the x and y components for each vector and figure out what the total is. So the x for A is 16 meters, so this is 16 meters. And then for B, it is, oh, I'm sorry, this is Y. Look at that, already messing up. Okay, so the Y is 19 meters for A and 6 for B. Goes up there, 6 meters. And then I'm gonna put the X just down one because this goes down further. So that is, this one is the 16, I think. Yes. Oops. 16 meters. And then B is 22 meters. 22 meters. And then C is 12 meters in X. And then Y for C is negative 30. Negative 30 meters. So now we can just solve this total path, or like the total displacement, by summing up the x and y components of each of these. So we could have done it without drawing it, but I feel like it's helpful to also see it. So I guess we'll call this D for displacement. D, the x component of D is going to be the A and B x components. So 19 meters plus 6 meters. And then we, I keep mixing up my x and y for that. So sorry. This is y. And then we're going to subtract 30. So that's going to give us negative 5 meters for y. And then for x, we just sum them up because none of them are negative. So 16 plus 22 plus 12 is going to give us 50 meters. So those are our x and y components of our displacement. dy equals negative 5 and dx equals 50. Okay. Now, one more example. So we have these vectors A and B, and we want to find what R is, which is the sum of them. So to do that, first, we want to take the x and y components of vectors A and B. So A, x and y. So A sub x is going to be A cosine 20 degrees. And A is 53 meters. So 53 meters cosine 20. This gives us 50 meters. We're rounding. 50 meters for x component. For the y component, we still have 53 meters, but sine of 20. And this one is 18 meters. And then for B, we have our x and our y. I think I can fit it. The x is, what is B? 34 meters. Cosine of 63 degrees. And this is 15 meters. And then y gives us 34 sine of 63, and that is 30 meters. Okay, so now we can just do what we just did previously and find the x and y components of this total vector R by adding those x and y components. So our x is going to be 50 meters plus 15 meters, which is 65. And then maybe I'll do y right here. The y one's 18 meters plus 30 meters is going to give us 48 meters. So, but that's not the magnitude, that's just the components. So magnitude can be a little bit confusing when dealing with vectors because it's either, well, I mean, it is just the length of them, but you have to find that. And that's where we use the, where it's like you're finding the hypotenuse. So the total R is the square root of the x component squared plus the y component squared. So this is the square root of 65 meters squared plus 48 meters squared. And that is 80.8 meters for R. And then let's see if this angle they're giving us here is correct. And we'll just solve for it. So let me draw. So what we found is we found the x component and the y component of R. And so to get the angle, we want opposite, which is y, over adjacent, which is x. So that's tangent of the angle is ry over rx. And then we take inverse tangent to get the angle by itself, and then tan inverse ry over rx, which is 48 meters divided by 65 meters. So let's check this one because I didn't calculate it ahead of time. So 48 divided by 65. So we get 36 degrees for the angle. 36 degrees. And I think that's, yeah, they say 36.6. I rounded down, but I got 36.4. So they probably didn't round the x and y components as much as I did. I like round numbers. Okay, cool. So those are examples. And then I have a video I want to show you and a little bit more to do, and we're all done. Okay, so I'm going to play you this video showing a ball drop where one of the balls is just going to fall straight down. And then the other one is going to have some horizontal velocity. And so you just want to look and see what happens when they fall. Oh, actually, I'm gonna turn the volume on because you're supposed to be able to hear them hit the ground. So, we'll see how that goes. Okay, so gonna release the latch and they're gonna fall. Right here. Let's watch that again. Okay. So you saw they, or heard, they hit the ground at the same time. So here is, well, here's a like graphic of this situation. And then here is like timestamp pictures showing this. But what you see is that it doesn't matter that one ball has some velocity and some motion in the x direction. It still falls the same way that the other ball does. So it shows us that vertical motion is independent of whether or not a ball is also, or the ball or an object is also moving horizontally. And this is because vertical motion is caused by that free fall acceleration due to gravity that we talked about, which is the same for each ball in both cases. So this tells us an important thing about solving problems of two-dimensional motion. Since the motion in the vertical and horizontal directions are independent of each other, we must solve for the motion in each direction separately. And we will practice this. just not today. But this leads us into the topic of projectile motion, which is this idea, which you could see with these traced trajectories with this, that it goes into like a parabola, and that is the shape of projectile motion. So if someone, for example, kicks their soccer ball at a certain angle, it is going to make this parabola as it moves both vertically and horizontally. And what we see in this, so they have some initial velocity at some angle, and then there's velocity in the x direction because of what we just did with the components. Because this is a vector at an angle. It means it has an x and y component. So there is an x component, and because with free fall, there's no, in general, if there isn't acceleration in the x direction, then this velocity is going to stay the same. And when we're working with projectile motion right now, that's what it's going to be. We're not going to have acceleration in the x direction. So you see this little blue arrow is the same the entire time because there's no acceleration in that direction. But then in y, we have this like orange arrow, and this behaves like how we talked about vertical motion, where it starts big and then it gets smaller until it gets to its very peak, and then it's 0, and then it gets bigger, but it has changed direction. Okay, so that's what we're gonna work on in the next lecture, but I just wanted to introduce it to you now. Okay, that's all. Have a great day.